Okay, good morning. So, we will get started today. Last time we had discussed about some very basic issues in real time operating systems, what are the basic requirements and so on. So, today let us build on that. Today we will try to examine the traditional operating systems, the popular ones being the Unix and the Windows. We will examine what are the issues if we try to use those traditional operating systems in real time applications. Actually, the idea is that this will give us an insight into how the real time system should be actually designed, what is really necessary required of them. So, let us proceed. Let us just recollect what we were doing last time. We were saying that the Unix system, which is possibly has the most profound influence on the entire operating system, is a monolithic operating system. In the Unix, we had said that all the operating system, most of the operating system services here, they operate in the kernel mode. The application programs, they run in the user mode and they can invoke the system service interfaces, which traps into the kernel mode and provides the required services. For example, there are 4 main categories of services that are available to the application program, dealing with tasks, creating tasks and so on, memory and device access, file access. So, all of these require trapping into the kernel mode and then providing the required service and then returning the result to the application program. In contrast, we had seen the microkernel operating system, which is also popularly used as a client server operating system, where the kernel implements the minimal functionalities. For example, task scheduling, memory management, some basic memory management and inter-process communication, these are supported in the kernel, and rest all other services are supported as user mode services through servers. So, if we try to look at a schematic of a microkernel operating system, we see that the microkernel only operates in the kernel mode and interacts with the hardware, and rest all other services which used to be in the kernel are operating in the user mode. For example, memory, here some very basic memory functionalities like the address space and memory protection are provided, rest everything here in the memory server, the process server, the file server, the display server.
So, then the file server has to directly interact with the hardware.
No, the file server through the microkernel. See, all these we did not show the interconnection. See, the client application is actually invoking the servers here, which are shown in the user mode, right, and these have to finally call the microkernel to interact with the hardware. These do not directly interact with the hardware. So, this we had said that this is the microkernel is the minimalist approach. The kernel provides only the very basic or core functionality based on which operating system can be built, and the elaborate functionality based on the core functionality provided by the kernel run in the user space. Typically, the functionality supported in the kernel mode is it varies from one implementation to other, but some mechanism for supporting address space and memory protection, because this is a basic requirement. Without this, the processes, the user processes and the system level processes, they will have it will become difficult to ensure memory protection. Some mechanism for CPU for allocating CPU to threads, that is scheduling basically. Some mechanism, I am sorry, I missed out here scheduling, mechanism for allocating or scheduling the CPU, allocating the CPU to threads, and then the basic inter-process communication mechanism. But we had said that the microkernel approach has become popular, but how does it evaluate? I mean, how does it compare with respect to a monolithic kernel approach? Let us look at the advantages first. One important advantage is that the microkernel approach makes operating system development simpler, because those who would have little bit tried out in kernel level debugging and programming, they would know that it is extremely hard compared to writing a user program. The main difficulties are there. The main difficulties are that do not have debugger which traps and stops at certain place and so on, reports you, because this itself is running in the kernel mode. And also if there is some data getting corrupted, it becomes very difficult to identify, because it can access any data, is not it? There is no protection here in the kernel mode. So the microkernel approach definitely will make the design and development much simpler, and it is especially advantageous in a multi-server system, as you were saying that in client server applications where the different servers run on different systems, it becomes advantageous. But there are disadvantages as well in the microkernel approach. For example, every operating system service takes more time to execute, it is expensive. Why is that? Because just making a single system call would require 2 function calls and 2 mode switches. Why 2 function calls? Yeah, exactly. There are 2 function calls necessary, because one to the server which operates in the user space, and that needs to again invoke the kernel, and similarly 2 mode switches are required. So it appears like a problem here. Actually, the initial microkernel operating systems like Mac and I think the Spring kernel, they gave very negative results as far as performance is concerned. The performance was much worse than a monolithic kernel, but the later generation microkernels, the performance is not all that bad as this shows, and especially for real time applications. The issue of importance is quick interrupt handling and robustness. If we have bugs in the kernel, can debug, then it is a big problem, because all these most of these are used in embedded and safety critical applications, and one of the primary requirement is robustness, and microkernel scores there. And also because the kernel is very small, the interrupt handling becomes quicker. Now, we had in some context I think discussed about the influence of Unix and how Unix developed and also alongside the Windows developed. So, if you look at it, I think 1968 or 69, the Unix system was developed at AT&T Bell Labs, we are told about that. And then in 1975, AT&T Bell Labs made Unix open, distributed the source code to whoever needed it. And then we had seen that Unix started developing from there onwards in different versions. The University of California, Berkeley, they developed the BSD, and then the IBM with AIX, HP with HPUX and so on. But AT&T also internally developed Unix further, and Unix system 5.4 released in 82. In between there are many other Unix versions, and this has become one of the popular and standard operating systems, Unix system 5.4. And then in the mid 90s, so here the PC evolution started. The PCs became extremely popular. Unix did not run on that, and the Linux was the attempt to make Unix run on the PCs. Unix is more of a server operating system, and then the Linux started evolving, and currently in version 2.6. But see here that the DOS started somewhere around 1981, 82 I think it was released, and after that there were several versions of DOS. Initially worked on floppies and then the disk, and then the Windows NT 3.1, which was I think another landmark here. The Windows appeared, the Windows 1.0 appeared something like 1986 I think, and then the Windows NT was a landmark here, we will see why, and then the NT 4.0, and then Windows 2000, Windows XP, Vista, and Windows 7. So, let us with that knowledge, let us try to see what problems would occur if the traditional operating systems are used in real time applications. If we take just a Unix or a Linux or maybe the Windows and then try to develop some real time applications, what would happen and why? We would examine also how difficult it is to extend or modify these traditional operating systems to make them real time operating systems. This investigation, that how to make the traditional operating systems into a real time operating system, will give us the clues to understand the working of the current real time operating systems, and also we can compare the features of the available real time operating systems. That will give us a better insight. Let us first look at the Unix system 5. If we want to use as a real time operating systems, what would be the problem? There are two main problems which we will notice. Anybody who wants to use Unix as a real time operating system. One is the non-preemptable kernel, and the other big problem will find the dynamic priority levels. Besides this, there are many other problems, but these two are the major problems that would be noticed. Now, let us look at the non-preemptable kernel. Let us investigate why this was necessary in the Unix, and can it be overcome, in what way. So, we had said that even a user program can execute in the kernel mode. How is that? How can a user program run in the kernel mode? Yeah, by making a system call, the user program runs in the kernel mode by using a software trap, right, a software interrupt. The original Unix developers did not visualize that Unix would someday be used in real time multiprocessor systems and so on. They were addressing the problem at that time, where they were more concerned about developing a time shared operating system. That was the in thing those days, right, time shared operating system and later virtual memory. Those were the focus those days, and they did not think that someday somebody will try to use Unix in real time or in multiprocessor systems. The origin of the problem of a non-preemptable kernel is that whenever it operates in the kernel mode, all interrupts are disabled. Why is that? Why should as soon as it starts executing in the kernel mode, all interrupts are disabled? Why is that? Anybody would like to answer this question? Why should they disable the interrupts as soon as it enters the kernel mode?
another interrupt occurs, we have to handle the interrupt.
Another interrupt occurs that needs to be handled. So, what problem would occur?
There are certain inconsistencies when the instruction is being executed and an interrupt has occurred. In OS level course, it's occurs.
No, as you were saying, when the interrupt occurs in the first level course, the currently executing instruction must be completed. That has to be, because after all instructions are atomic. You can't just stop it halfway and then start. Current instruction.
But if in a higher level program, a single statement is broken up into several instructions.
Yes.
And in a single statement like some A is equal to B, it is split into 3 or 4 machine level instructions.
Yes.
Now, executing that instructions, before updating the variable A, if it gets interrupted, then parallel programs get affected.
Not really. It is not that complicated. The thing is that in kernel mode, every data is available to every process, every kernel code, and if one kernel process has halfway modified a data, and then there is an interrupt and there is a new process starts coming, kernel process starts executing and modifying this data, the kernel data becomes inconsistent. That is the main problem. The kernel data becomes inconsistent when one kernel code is interrupted and another kernel code starts operating on that. And of course, somebody can use locks, right? If a process has not completed using some data, can use lock, but disabling the interrupt was an easy and efficient way to preserve the integrity of the kernel data. Before the kernel mode completes, no other process can change it. And of course, that time the requirement of before the kernel completes another interrupt being handled did not arise, kind of applications they had envisaged those days. So, the main problem why they made kernel non-preemptable, that is masked all the interrupts when it is in kernel mode, is to preserve the integrity of the kernel data. That was the simplest thing to do. Let the current process complete, and then only another process can start. But in a real time application, a non-preemptable kernel can cause deadline misses. Why is that?
When a higher level task comes, it doesn't interrupt the lower level.
Right. It needs to complete the current processing. So, if we look at the preemption time, the task preemption time, that would become the time spent in the kernel mode, because this cannot be interrupted. So, the time spent in the kernel mode plus the context switch time, and the time spent in kernel mode can be a second or even more. So, it can be even more than a second in the worst case, and second granularity in real time applications clearly not acceptable. We need microseconds. That is the preemption time which is expected, and if it is second, no way it can run hard real time applications. Now, let us look at the dynamic priorities. What is the origin of the dynamic priorities, how the priorities change dynamically, and why it is needed? The Unix scheduler maintains a multi-level feedback queue. See, there are different priority processes here, starting from the user level processes to the kernel level processes, and then the file handling, buffer, disk IO, swapper, and so on. And at each level, there are tasks or processes that are queued up. One of them executes until its time slice is over, and then it gets feeded back to the same level or maybe at a different level, right. So, this is the multi-level feedback queue. There are multiple queues here, multiple levels of queues, and each of them there is a feedback mechanism after the time slice, just gets reinserted into the queue. the system by default uses a 1 second time slice. So, after 1 second it gets reinserted back into the queue. Of course, this is a configuration operating system configuration parameter, you can change from 1 second time slice, but if you just install Unix and start using it, it uses a 1 second time slice, because there are advantages of using a smaller time slice, larger time slice and so on, which are covered in a first level course. And after a task completes its time slice, its priorities are recomputed. So, a task at the lowest level here in user, it might just come to a higher level, or a higher level process might go into a lower level. Of course, a user level process will not become a kernel process, it will not go to that priority. The kernel processes operate at a higher priority. Actually, we will see that it is not even that simple, there are priority bands. Okay, we will just discuss that little later. So, let us look at the scheduling policy that is used. It is used in Unix, this is the policy, but a small variations of this or in slightly different flavor is used in all other operating systems, including Windows. So, let us look at this. The priority of a task Ti at its jth time slice is the CPU utilization. It is actually a history of CPU utilization of the task Ti at this instant, that is a history of CPU utilization divided by 2 plus some base priority and some nice value. And see here the history of CPU uses, this is actually defined recursively. The CPU history of CPU utilization by task Ti at jth instance is utilization in the last instance, the CPU utilization. You use the CPU utilization in the last time slice that just got completed, that has half priority, that is 50% weightage, and its history before that, that is from its first time slice to the j minus 1 time slice, is given half the weightage. So, we will see the implication of this. So, PRTij is the priority of the task Ti at the jth instance. CPU Tij is the history of CPU uses by Ti, and we will see that this translates, this formula of priority computation translates into a geometrically decreasing weight for the history of CPU utilization.
What is that nice?
We will come to that. We will see what are the components here, the base priority and the nice priority, why they are there, we will see that. Utij is the CPU utilization in the jth instant, that the jth time slice it has got. So, how much jth time slice is the last time slice it utilized, right. So, last time it was allocated CPU, how much CPU it could use? Could it use the entire time slice, or could it just use a small fraction of it? Why can't it utilize the full time slice? Yeah, no, see, it can block itself, right. When it performs IO or waits for some condition, it changes its state from executing to waiting. I think those are the first level operating system course, that when a task waits for something, for a page fault or for some IO to occur, file IO, or maybe waiting for some other condition to occur, it relinquishes the CPU. And the base component here, the base Ti, is used to separate the different tasks into bands. That is what we are saying, that the different tasks are segregated into bands, the user tasks into several bands and the kernel tasks also into several bands. We will just see that what are the bands. and the nice Ti is a value set by programmer when creating a process. If you look at the Unix system call, a fork or something, you will see that you can specify a nice value. Nice, as the name says, you can be nice to the other processes and decrease your priority, your task. The programmer can decrease his task's priority by setting the nice value to a plus some value, and negative nice value is not allowed in the user mode. So, a user mode program can only be nice to other programs, let them execute at higher priority, and this can execute at a lower priority. Now, let us see this history of CPU uses, because that was one important term there. Besides the base and the nice values which are constant, the history of CPU uses was the main term there. So, this was the term actually. The history of CPU utilization by task Ti at the jth instance is defined as half the weightage to the utilization in the last time slice, whether it was 100% or 20% or whatever, that is given half the weightage, and all other time slices before that are given the other half weightage, 50% weightage to this and 50% weightage to this. As we are saying that this is a recurrence relation.
Should that not be that u Ti j minus 1, because you are telling us the previous.
No, Tij is the jth time slice that just got completed.
And CPU Tij, that is also the same.
This is CPU Tij is the history of CPU utilization at the completion of the jth time slice. Okay. So, this is the utilization that occurred in the last time slice plus the history of CPU utilization that existed or that exists at the completion of the j minus 1 time slice. Now, this is a recurrence relation. See here, CPU Tij is defined in terms of CPU Tij, right. Now, whenever we have recurrence relations, we know from my first level knowledge in mathematics, we need to unfold the recurrence. So, so this should have been unfold the recurrence, it's a mistake here, or maybe recursion, I do not know what I wanted to write, it should be a recurrence. So, see here, if we unfold it, so CPU Ti j minus 1 by 2, we can write in terms of u Ti j minus 1 by 2 plus CPU Ti j minus 2 by 2, right. We can substitute this here, and then we will get, by substituting this one here, we will get u Ti j by 2 plus u Ti j minus 1 by 4 plus CPU Ti j minus 2 by 4. Is that okay, or should we need to do that? It is clear to everybody, right. So, that is by just one level of expansion, we can keep on expanding that. So, we can get this relation CPU Tij is u Tij by 2. So, that is the CPU utilization in the last time slice has 50% weightage. The utilization at the time slice just before that, it is the j minus 1th time slice is given 25% weightage, j minus 2 time slice is given 12.5% weightage, and so on. This is geometrically decreasing weightage to the history of CPU utilization. But what is the motive? Why do they do this? Let us investigate that, because as we were saying that it is not that the Unix does this, but every other traditional operating system does this. They recompute the priority at the end of a time slice. Okay, before that, before we look at why they do that, let us understand the base priority and the nice values. The base priority segregate tasks into bands. For example, the kernel tasks are segregated into swapper, block IO, file manipulation processes, character IO processes, and the kernel process. and then the user process. These are the bands. So, all the tasks that are there in the system are segregated into these bands. See here, this is the user band, this is one band, user level n to user level 0, then we have the kernel processes, and then these ones to handle different types of I/O, the character I/O, file I/O, block I/O and the swapper. What is the difference between character I/O, file manipulation, block I/O and swapper? Can anybody give an example of a character I/O?
Keyboard.
Yeah, keyboard is a character I/O, exactly. And what about block I/O?
File being transferred from hard disk to the RAM. Block of data is being transferred.
DMA also.
Yeah. In block I/O, you perform blocks of data transfer, for example, in a DMA. So, where DMA is useful? When DMA becomes useful? I mean, just give one example of operation where DMA is used.
When one system transfers data, DMA transfer it can be.
You mean to read out onto the media?
Yes.
Yeah.
Or even that when you are outputting this data to printer, then that can be put DMA.
Read data to printer,
Writing data to printer.
writing data to printer, but printer is, I mean, you mean a printer has a buffer there and the buffer is written, is it?
Yes.
Because if it is takes a character at a time, DMA cannot occur.
Yes.
Okay, one of the most popular example, very popular example is a page fault. A page of data is transferred. Okay, that is a popular example of a block I/O is a page fault. But what about swapper? Yes, anybody like to? No, that is page fault. You mean?
When page fault occurs, you have to swap. One you have to put one out, one page out, and
No, it does not occur like that. No. See, when a new page comes, right? You, if the current, if there is a block available there, just write on that. And if block is not there, you replace it, and it does not get written immediately. It need not be written immediately, right? It does not occur like we have to swap one page, bring in one page and at the same time write. No. What is a swapper? What is the swapper functionality in an operating system? You have a component there called as a swapper, if you have heard. See, if a task, if a user task remains inactive for a long time, it is swapped. All its context and all its pages are swapped out from the memory. So, here multiple pages are swapped out.
Only when another process needs memory.
Not really, see, dormant processes which are inactive, it determines when a process becomes inactive.
So it will periodically check whether the some processor are active or
The operating system checks whether a process is active. If it is a dormant process, it is swapped out. If you check the status of processes, if you give a listing of processes and then see, you will say that it will show some of the processes are swapped out because they are inactive, they are swapped out, and here multiple pages needs to be written at the same time.
Will it swap or will it terminate the process?
It swaps them out unless the process itself terminates, it does not. It swaps them. An inactive process, yes, exactly, it just frees the memory. All the pages of a inactive process are swapped. But then after having understood that, why is these priority bands ordered in this way? Kernel process which do not do I/O, then see here character I/O, file I/O, block I/O, and then swapper. Why swapper at the highest priority, then block I/O next highest, file IO, then character IO at a lower priority, and then the kernel process among all the kernel processes.
And the memory is full.
No. The question is that why is this priority allocation into bands here? The swapper is the highest priority process. Block IO next, file IO next, character IO next, and the kernel process is not requiring IO. They operate at this level. Why is that? Of course, one thing you can notice is that higher amount of data are handled by this. Character IO just handles some characters of data, this larger amount of data, this is blocks of data in this entire address space of a process. Okay, so let us investigate that issue.
Because they have to release more amounts of data than much. Swapper has indulged with more amount of space with inactive portion.
So why should it get a higher priority? It definitely deals with larger data as we proceed from here. These
Get rid of it immediately.
not really. Let us investigate, because that is the crux of the problem we need to understand, and that will become useful throughout our other discussions in these operating system, real time operating systems. The central idea in all traditional operating systems, including Unix and Windows, is that the IO operates at a very slow speed compared to the CPU speed. We know that the IO is typically 1000 times or maybe tens of 1000 times slower than CPU. CPU operates at gigahertz, that is the CPU clock cycle, but IO milliseconds, even the fastest IO. So, in every operation that you analyze, the time taken by a process to complete, IO is the bottleneck, and we are in a traditional operating system, we are concerned with the average throughput, right. That is the most important parameter in traditional operating system, is average throughput. How many processes could be completed, how many tasks could be completed per unit time. So, since IO is the bottleneck, the IO channels should be kept as busy as possible. Do you agree with this? See, IO is slow, so the operating system should try to maximize utilization of the IO channel. If a process is trying to do IO, it should be given the highest priority. Do you agree with this? Okay, so some of you do not seem to be very convinced, but let me just tell you a small story or instance. See, suppose you want to write down something from a notebook. Okay. Now, you ask one of your friends to read out the book or something, and the other person just keeps on writing. Two persons who are helping you out, one is reading out the book and the other is writing. Now, let us say once in a while they just doze off and they waste some time. So, if you want it to be done at the shortest time, would you watch the person who is reading or the person who is writing? See, the person is reading very fast. Okay. Now, if he is reading, the person writing, he cannot even complete before he reads one sentence, and he pauses, right, anyway, and the writer is the one who is crucial. If he pauses, then your work will get delayed by that time. So, you have to watch the person who is writing. If he is writing always, is not dozing off and so on, then he will complete it the fastest. That is the basic idea here. So, the IO channels should be kept as busy as possible, and how do you ensure that? Increase the priority of IO processes. So, to increase the average throughput, raise the priority of IO intensive tasks. A kernel process which is not doing IO should operate at the lowest priority, and then we have the character IO, etc. But why should it translate into dynamic priority level? See, this same idea that a task performing IO should be given higher priority. That is the idea with which the user process priorities are recomputed after every time slice. Dynamic recomputation of the priorities after every time slice. This is also the idea. Anybody would like to guess?
CPU incentive.
Yeah, exactly, clear. Yeah, the CPU intensive tasks who utilize their time slot completely, they are the CPU intensive tasks. So, they should be given lower priority. The ones that are doing I/O, they could use only part of their time slice, their priority should be increased, so that they will do more and more I/O and they do not have to wait. The processes doing I/O should operate at a higher priority, and those which are recently been doing processing, their priority should be reduced. So, the I/O bound processes, they gravitate towards higher and higher priorities. The more and more a process does I/O, the Unix or Windows, they will ensure that its priority successively becomes larger and larger. Of course, there is a limit, they can't really cross over from one band to another. A user band process cannot become a kernel band process, or a kernel band process cannot become a character band process. They operate within their own bands, priority bands, but their priority increases or decreases. But in a real time situation, if a real time task spends much of its time in computation, then its priority will decrease and it will miss its deadline, and this is not acceptable, because the programmer is the one who should decide at what priority a task should operate. That was the basic thing that we studied in the RMA or EDF. It is based on the deadline requirement that the priorities are computed, rather than whether they are doing I/O or using CPU. So, this is unacceptable for hard real time applications, will definitely lead to many deadline misses. So, Unix 5, system 5, if we try to use this as a real time operating system, we will see that it is suitable only for soft real time applications, where the deadlines are of the order of several seconds, because the kernel level can make the non-preemptable kernel can delay it by a second, and then these priority manipulations. So, it can be off by several seconds. So, if we are talking of a soft real time task where the deadline itself is tens of seconds, then Unix can be used. But when the deadlines are of the order of milli or microseconds, obviously you can't use Unix 5, it will only lead to failure. So, the main deficiencies of Unix, if we summarize, one is that the task preemption time is of the order of a second. Dynamic recomputation of priorities, and then we have the resource sharing problem. We did not tell about that, but that is also another problem, because if a low priority process is holding the resource, then the higher priority process will keep on waiting for it. So, the task preemption time is order of a second, because preemption is disabled during system calls. There is dynamic recomputation of priorities, because the goal of traditional operating system is to increase the average response time for tasks, rather than letting tasks meet their deadline. And the resource sharing problem is that a high priority task may wait for a low priority task to release its resources, and priority inversion can occur. There are other deficiencies of Unix 5. See, those three are the main. There are many other deficiencies. For example, interrupt processing is inefficient. It takes several milliseconds for interrupt to be processed. Unsatisfactory support for device interfacing, unsatisfactory timers, lack of real time file support. These to some extent can be overcome by doing some extension to the Unix kernel, simple extension. As we were saying that a real time file support, basically the file needs to be written in contiguous area in the disk, and also the space for the file needs to be pre-allocated, because if it is written halfway and finds the disk cannot support, then there will be a failure. So, this can be supported, even these to some extent by simple extensions to the operating system can be supported, but those three are the main problems that needs to be handled before this can be used for real time applications. So, we examined the Unix as a real time operating system. Now, let us do the same thing for Windows, because sometimes because of availability of Windows, easy availability on desktops and so on laptops, we might attempt to use Windows as a real time operating system. One thing that we should know is that after Windows NT, the system has become stable, it does not crash unnecessarily, whereas before the NT series was the 98 series, where it would just crash for no reason. For example, you were doing a Microsoft Word application and suddenly see that the screen has frozen. It is not that you by mistake click. The normal users think that did I do something wrong, did I click the mouse 2 times or 3 times, what caused the problem? No, those are not the person who is using his problem, it is the bug in the operating system which made it crash. So, before 98, Win 98, it was unstable, it will crash for no reason, basically bugs in the operating system. But then the NT series came up after that, and we are all using the derivatives of the NT series, which is much more stable, and you can think of these as being used in real time operating system. An unstable operating system can't use for real time application or safety critical application. And we have POSIX support for Windows. We will shortly see what this means, the POSIX support, and then it supports multi-threading. Some good features are there for Windows. Now, let us see what are the difficulties that might occur if we use Windows for real time applications. But before that, let us look at little bit inside the Windows, just like we did for Unix. The Windows, if you look at it, has evolved over the last 30 years from a very simple disk operating system, which was kind of a toy operating system where every task can do anything. You can even delete the operating system itself. It has evolved from there and has become a dominant operating system nowadays. The DOS, as we were saying, was developed in 1981, released in 1982. Very simple operating system. The DOS those days, to single tasking, used segmented memory management. And then the Windows appeared 1986. The main distinguishing feature of the Windows from the DOS was a graphical front end. Initially, the Windows was also single tasking, but it was a graphical front end, which was one of the major innovations of the Windows operating system. Unix lacked that, and they even did not support it until the Linux supported a graphical front end. New versions of the Windows kept on appearing very frequently, every year 2-3 releases, through enhancements to the DOS code. And you know, if you have a code, a DOS code or something 82, and you keep on changing it each time, trying to add new functionality, fix the bugs and so on, it will become a bad code. Any maintained code becomes a bad code, and the structure of the code degenerated after every time the code was changed to bring a new version. And then it became very difficult to debug and maintain the code, and it is said that in Windows 95, 50,000 known bugs existed. They have been reported, but they could not be corrected because the code is so hard to correct it. No, it's become, the structure is really bad, 50,000 known bugs, and definitely it was unstable. Use Microsoft Word and just clicked and it crashes and that kind of thing. Of course, these could not be used for real time applications. So, if you look at the evolution, the DOS in 1982 and kept on evolving, finally appeared Windows in Windows 1.0 in 1986 and then Windows 3.x, Windows 95 and Windows 98, and here this code was junked. And alongside this, a new code was written from scratch, that is the NT code. The NT code was written here alongside here just before Windows 95. Something around 1993, the Windows NT 3.1 was released parallelly with the Windows 95, and Windows NT 4 is the Windows NT that we know popularly, and from there the derivatives Windows 2000, Windows XP, Vista, Windows 7, etc. kept on appearing. So, the Windows code was completely rewritten in the NT system, Windows NT, and it used microkernel design, but if we really analyze it, it has layers, it is more layered than actually a microkernel. It has a small microkernel and there is a executive, as we will see in the diagram. The Windows NT system is much more stable than the DOS based systems, needless to say, because we will see that the microkernel designs, it is much more easier to develop, much more easier to handle bugs, because they are user level processes, most of them, remember, only small kernel, and debugging kernel code is difficult, but debugging user level process is not a problem, and definitely the NT system became stable with the partly microkernel design. And the later versions of Windows that became available are descendants of the Windows NT, and the DOS based systems were scrapped. As we will see that the NT microkernel provides very basic services just like any microkernel, and then there is a executive, the Windows NT executive, which builds on the base services provided by the microkernel to provide user level services, and these user level services are used both by the operating system, that is the privileged subsystem, and also the user programs. They invoke the user level services provided by the Windows NT. So, I think we will just examine little bit about the way the NT operates. I think I have a diagram here. Okay, yeah, we will see the executive microkernel and the Win32 and the POSIX interface, and today we are running out of time. So, next class we will look at Windows NT, the basic features just like we looked at Unix, and then see that what are the difficulties if we use it as for real time applications, and how it can be extended or how it has been extended by Microsoft to provide WinCE, which is for real time, which is the real time operating system from Microsoft, the WinCE, whereas in Unix there are many variants of Unix which are based on the basic Unix and trying to make it suitable for real time applications. So, we will stop here and meet in the next class. Thank you.